Hello again, everybody. In this lesson today, we are going to talk about translations of graphs, and then we're going to end up with some compression and stretching of graphs. So what does a translation mean? Well, it really just means shifting the graph either horizontally or vertically, okay? So if I have a graph and I draw it on my XY axis, and let's say this graph is maybe a parabola, okay? We'll start out with something real simple here. And I have a graph that looks like this. Now this, for just our demonstration purposes, we'll call f of x is equal to x squared. Now, the simplest of all the translations is the vertical translation, and that just simply means shifting my graph up or down, okay? So if I want to say shift this graph up, we're just talking about changing the y value, aren't we? We're not going to worry anything about the x value. So if this is f of x equal to x squared, then my green parabola, notice all I've done is take each point and move it up, haven't I? So I've changed the y by increasing it. So if my original was f of x is equal to x squared, and I know in translating this graph up, I'm changing the y, all I've really done is add some constant c to this. Because remember, f of x is y, isn't it? All I did was change the y values in this graph. So I added something. The normal f of x would have given me this value. I'm just going to add it. And this shift here, this translation, is that amount c, okay? So if I can shift up, then I can certainly shift down, can't I? So here, I'm moving my graph down, right? My graph down. So everything is just shifting down. So if I look at this particular graph, and I know my original was x squared, my shape isn't changing, just this y coordinate. And if we call this distance here c, then all I've really done is I've gone ahead and calculated the original graph the way I would have, and then I've changed where the y value is. So here I've added c, and here I have subtracted c, okay? And this works for really any kind of function. If I had a graph and it had just some shape to it like that, well, I could shift this up, couldn't I? Or I could shift it down. So either way, it still becomes y is equal to f of x minus c, because y was equal to f of x, which means in the shift up, y was equal to f of x plus that constant c, okay? So here is the value c. Here is the value c, okay? So any kind of shape can be moved up or down when we're doing these vertical translations. So if we can go vertical, we can go horizontal. These will not initially seem as intuitive as the vertical, okay? So we'll start off with our parabola because it's easy to see. And we're going to call this guy f of x is equal to x squared, okay? So let's say I shift this guy this direction, okay? So here's where I'm going to explain to you it's not as intuitive. Because what I want to do here, and I already started to write that incorrectly for you, so let me erase that. So if I have my f of x function, and so I'm just going to use y is equal, what is the new function? Here's where it's not as intuitive, okay? Notice I shifted left this amount, c, okay? But in my notation here, I'm adding c. So what you have to think of, if I'm shifting left, I'm adding the change, but that's because, notice, if I went here and I'm graphing this one, I would have said it looked just like this one, which meant I added the c, okay? So if I'm graphing the shift, I'm looking at what it would have looked like, okay, which allows me to make this shift left. But I need to think of adding c in order to get that graph, okay? So if I shift my graph to the right, so I've come over this distance, okay? Well, now let's look at that. So y is equal to f of x minus c. So here again, if I'm going to graph my graph that's shifted to the right, what does it look like? Well, it looks just like the graph that is to the left, and to the left means I would have had to subtract a c, okay? So f of x is here. If this is my new f of x, right, my new x value, in order to graph it, to shift it, I can look back the minus c to see what it would have looked like, okay? So that's how we can do some of these shifts left and right and up and down on these graphs. So let's say we had a graph and it looked like, how about it looked like this? And I wanted to shift it left. So y is equal to f of x. And let's just say, we'll go left 2. So I would be adding 2, which would mean my graph would look something like that. Now this should be kind of be parallel, right? So if I wanted to shift it to the right, I'm going to have to subtract 2. And so I should get this shifting to the right. And it really should be a little more like that, okay? Just to get an accurate picture of what this is looking like. So to the right, I subtract. To the left, I add. So there's one other kind of translation that we can have. And let's just do our parabolas because they are so easy to work with. So f of x is equal to x squared, all right? So let's do this particular. F of, or y is equal to f of x plus 3 minus 2, okay? 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. So what have I done here? I've combined the vertical and the horizontal, right? So my vertical is this term out here, because remember when I was doing the verticals, I was adding and subtracting. And this is the one that was intuitive, right? If I added, I shifted up. If I subtracted, I shifted down. So here I am coming down, okay? So I'm looking at this point right here. If all I was doing was a vertical. Now I'm adding x plus, using x plus 3, right? So when I add, I go left. So I'm going to take this point here. I'm going to come down 2. I'm going to go over 3. And he's going to be right there, okay? So every single point is going to come down 2, go left 3. And I'm going to have this new graph. Same shape, but look what has happened. This guy has actually moved diagonally, hasn't he? So when I'm combining both the vertical and the horizontal, I have a diagonal shift. So if I added 2, I would have gone up 2, right? Here would have been the vertex of my parabola. If I had subtracted 3, then everything moves to the right, doesn't it? So if this was minus 3, I would have come down 2, gone over 3. You know, and the same kind of thing. So when I'm shifting my graphs, vertical is intuitive and horizontal, sometimes it just wants to seem a little counterintuitive, right? So if I add, I go left. If I subtract, I go right. Okay, so that's about translating graphs. And the other thing I wanted to talk to you in this lesson about is compression and stretching of graphs. Because we can do certain things to our graphs that cause them to change, okay? So let's take a look at something where we can really see easily what's going on here, okay? So we're going to take a graph and we're going to use the absolute value graph. And it's a nice 45-degree angle graph here, okay? So this here is f of x is equal to the absolute value of x. All right, so I'm just saying y is always going to be the positive of whatever x is, right? So if I come over 4, I'm going to go up 4. If I come over 2, I'm going to go up 2. If I go left, where I'm going negative x, I'm still going to get a positive y. So this is the absolute value graph when we look at it, okay? So we've got a couple of other types of things that can take place. So let's talk about the first one, and that one is stretching. Well, when I'm stretching a graph, okay, I'm taking that particular graph f of x, whatever it is, and I'm going to multiply it by some constant c, where c happens to be greater than 1. So if I multiply my graph, so my x doesn't change, but say x was 3, and I multiply it by something, it's going to get larger, isn't it? So my x, my y value, when I am stretching, is going to get larger for each x value, okay? So you want to think in terms of I'm stretching away from the x-axis, okay? So that's what stretching is all about. This is taking f of x and multiplying it by some constant value, but the important part is c has to be greater than 1, okay? If c is equal to 1, then I get the original function, don't I? Because 1 times f of x is still f of x. So if I'm using the absolute value graph, I'm stretching away from the x-axis, okay? So I've got stretching and I have compression, okay? And compression, it's the same formula, some constant times f of x, but now c is less than 1, and, oops, got that too close, didn't I? And it is greater than 0. So what am I talking about? C is some kind of fraction, okay? So now my new graph, if I'm talking about absolute values, is going to look something like this, right? So compression, if you thought of this as the x-axis is the ground and the y-axis is straight up, then we're compressing it down towards the x-axis. So here I have taken it and I have compressed it down towards the x-axis. Here I have stretched it away from the x-axis, okay? So compression is this flattening, and stretching is this moving away from the x-axis. But here's the keys. It's the same formulas, but it's all a function of what c is. So if c is greater than 1, I'm going to be stretching. If c is some sort of fraction, I'm actually going to be compressing that graph, okay? So I can do these sorts of things with all sorts of equations. Let's really make up one here that combines a lot of this, okay? So let's take our trusty parabola, and so we know this here is y is equal to f of x, which is equal to x squared. So what if I have this? Y is equal to 1/2 of f, let me change that to a bracket, f of x plus 1 minus 3. Boy, I can't get my brackets right today, can I? Okay, so, and you know what? I really don't want it that way because I just want this fraction out here to apply to this function. So 1/2 times f of x plus 1 minus 3. So what have I done here? because now I've combined everything. So I have moved down. I've translated it vertically 3 units. And I have shifted left 1 unit, okay? So my new vertex actually belongs here, doesn't it? So I've made this shift here. So this takes care of the shift, but now what do I have to do? I look at the fraction, I'm compressing. So instead of it being this mirror image here, now it's going to look different, isn't it? So it's going to get flattened out. It's getting compressed, you know, because this now functions as the new x-axis, doesn't it, for this guy? So I've compressed it, I've translated it vertically and horizontally. Okay, now right here, you know, all of these things I've been doing so far have been all estimates. I'm really just wanting you to understand the theory behind all of this because, you know, obviously I can take values and plug all of this in, can't I? And plot it point for point, but it's really important to understand what you expect the graph to look like. So what have we covered in this lesson? Well, we've covered translations, horizontal and vertical, okay? So if I'm going to go up, I add. Down, I subtract, okay? Straightforward and I think intuitive. If I'm going to move horizontal, well, this is where I have to think a little bit harder. So if I'm going to move to the left, I'm adding to the input value to my function. If I'm going to move to the right, I'm subtracting from my input value of my function. And then I can obviously do both. I could shift vertically and horizontally on my graphs. Then we introduced the concept of compression and stretching and thinking in terms of compression, flattening or moving towards the x-axis for that function, and stretching, moving away from or increasing, you know, the y values, if you will. And then we did an example right here at the end where I can do all of that to just one graph. Vertical, down here. Horizontal, I moved left because I was adding. And then I flattened because C was a fraction, okay? If C had been greater than 1 here, then this guy would have been a much narrower parabola than what you see here, okay? So those are the things I wanted to talk to you about on translations, compression, and stretching. So I will see you guys next lesson.